What if 1 billion years ago life had already begun? What if life didn't begin on Earth the way we think it did? What if 1 billion years before us, long before the oceans settled, before the continents formed, life had already started, somewhere else, or perhaps even here, in a world we can no longer recognize? Close your eyes for a moment and imagine standing at the edge of time itself. Not human time, measured in centuries or millennia, but cosmic time, the kind that stretches so far back that our entire civilization becomes nothing more than a whisper in the dark. 1 billion years. The number itself feels impossible to hold in your mind. If you tried to count backward, 1 second at a time, you would need more than 30,000 years just to reach 1 billion. And yet, when we speak of life's origins, we're speaking of timescales that dwarf even that incomprehensible span. The story we've been told is familiar enough. Earth formed roughly 4.5 billion years ago from the swirling debris of a young solar system. For hundreds of millions of years, our planet was a hellscape. Molten rock, toxic atmospheres, asteroid bombardments that would have vaporized anything resembling life. Then, slowly the surface cooled. Water vapor condensed into rain that fell for millennia, filling the basins that would become our first oceans. And somewhere in those primordial waters, perhaps in a warm tidal pool or near a hydrothermal vent deep beneath the waves, the first spark of life ignited. But what if that story is incomplete? What if the timeline we've constructed, careful, evidence-based, built on layers of geological and biological discovery, is only showing us the most recent chapter of something far older? What if life didn't begin 3.5 billion years ago in Earth's ancient seas, but had already been unfolding for eons before that moment, in places and forms we can barely imagine? Tonight, we're going to explore that possibility, not as fantasy, but as a genuine question that sits at the intersection of science, cosmic history, and the deepest mysteries of existence. We're going to journey backward through time, past the familiar landmarks of evolution, past the formation of our planet, into epochs so remote that even the rocks have forgotten them. And we're going to ask whether life, in some form, in some place, might have been waiting there all along. The night is quiet, the stars are watching, and the story we're about to tell stretches across distances that make the human experience feel like a single heartbeat in an endless song. To understand how radical this question truly is, we need to first understand what we think we know about life's beginnings. The scientific consensus, built on decades of research, places the emergence of life on Earth somewhere between 3.5 and 4 billion years ago. The evidence comes from multiple sources: ancient rock formations in Western Australia and Greenland that contain what appear to be fossilized microbial mats, chemical signatures in ancient minerals that suggest biological activity, and the molecular clocks embedded in the DNA of every living thing, which allow us to trace backward through evolutionary time toward a common ancestor. These earliest life forms were nothing like what we see around us today. They were simple, single-celled organisms, bacteria and archaea, that thrived in environments we would consider utterly hostile. Some lived in scalding water near volcanic vents. Others survived in acidic pools or beneath thick ice. They didn't breathe oxygen because there was almost none in the atmosphere. Instead, they metabolized sulfur, iron, methane, whatever chemical gradients they could exploit to extract energy from their surroundings. For billions of years, this was the only kind of life Earth knew, microscopic, invisible to any hypothetical observer. And yet, these organisms were performing one of the most important transformations in planetary history. Some of them, the cyanobacteria, learn to harness sunlight through photosynthesis, splitting water molecules and releasing oxygen as a waste product. Slowly, over hundreds of millions of years, they change the composition of the atmosphere itself, creating the oxygen-rich air that would eventually allow complex life to evolve. This is the story we tell. It's elegant, well-supported, and revolutionary in its implications. It tells us that life emerged relatively quickly after Earth became habitable, that it adapted to extreme conditions, and that it fundamentally reshaped the planet it inhabited. But here's where the questions begin to multiply. If life appeared so quickly on Earth, within a few 100 million years of the planet cooling enough to support it, doesn't that suggest that the emergence of life might not be as improbable as we once thought? And if it's not improbable, if the conditions that spark life are relatively common in the universe, then why would Earth be the first place it happened? Our Sun is a relatively young star, born about 4.5 billion years ago, but the universe itself is nearly 14 billion years old. For almost 10 billion years before our solar system even existed, stars were being born and dying, planets were forming and evolving, and the basic chemistry of life, carbon, hydrogen, oxygen, nitrogen, was being forged in stellar furnaces and scattered across the cosmos. What was happening during all that time? Were those billions of years simply empty, waiting for Earth to arrive on the scene? Or is it possible that life had already begun its journey long before our world took shape? The question opens like a door into darkness, and beyond it we can glimpse possibilities that challenge everything we assume about our place in the cosmic story. To explore this possibility seriously, we need to understand what life actually requires. At its most fundamental level, life is a chemical process, a self-sustaining system that can extract energy from its environment, maintain its internal organization against the natural tendency toward disorder, and reproduce itself with enough fidelity to preserve information across generations, but enough variation to allow for adaptation and evolution. The building blocks of this process are surprisingly simple. Carbon atoms, with their ability to form complex chains and rings, provide the structural framework. Water serves as a solvent, allowing molecules to move and interact. Energy, whether from sunlight, chemical reactions, or heat, drives the processes forward. And time, vast stretches of time, allows for the trial and error of chemistry to stumble upon combinations that work. None of these ingredients are unique to Earth. Carbon is one of the most abundant elements in the universe, forged in the hearts of dying stars and scattered through space when those stars explode. Water exists throughout the cosmos, frozen on distant moons, locked in asteroids, floating as vapor in the atmospheres of planets we'll never visit. Energy sources are everywhere, from the radiation of stars to the tidal forces between moons and planets, to the chemical gradients in subsurface oceans. If the ingredients are universal, and if the basic chemistry of life follows rules that apply everywhere in the universe, then the emergence of life becomes not a miracle unique to Earth, but a natural consequence of cosmic evolution. And if that's true, then the timeline of life's origins might extend far beyond our planet's history. Consider this. The first stars formed only a few 100 million years after the Big Bang. These were massive, short-lived giants that burned through their fuel quickly and exploded, seeding the universe with heavier elements. By the time the universe was 1 billion years old, second-generation stars were forming from clouds enriched with carbon, oxygen, and other elements necessary for life. Planets were coalescing around these stars, and on some of those planets, conditions might have been right for chemistry to begin its slow dance toward complexity. A billion years ago, from our perspective, Earth was already ancient, home to simple multicellular organisms with oxygen in the atmosphere and continents beginning to take recognizable shapes. But a billion years after the Big Bang, the universe was still young, still wild, still experimenting with what was possible, and somewhere in that vast cosmic laboratory could life have already begun? The idea isn't pure speculation. It's grounded in what we know about the universe's timeline and the distribution of life's building blocks, but it requires us to expand our imagination beyond the familiar story of Earth's origins and consider the possibility that life's first chapter was written in a place and time we can never directly observe. What would that early life have looked like? Would it have resembled the bacteria and archaea that dominated Earth's early history? Or would it have taken form so alien, so adapted to conditions we can barely imagine, that we wouldn't even recognize it as life if we encountered it? These questions lead us deeper into the mystery, toward ideas that blur the line between science and philosophy, between what we can prove and what we can only wonder about. One of the most compelling frameworks for understanding how life might have spread across cosmic timescales is the theory of panspermia. The word itself comes from Greek, pan, meaning all, and sperma, meaning seed. The idea is ancient, appearing in various forms in the writings of Greek philosophers, but it was given scientific credibility in the 20th century by researchers who recognized that life might not be confined to the planet where it originates. The basic concept is elegant. Life, once it emerges, is remarkably resilient. Microorganisms can survive in the vacuum of space, endure extreme radiation, and remain dormant for millions of years. If a meteor strikes a planet with life, it can blast rocks and debris into space, carrying with them any microbes that happen to be embedded in the material. These rocks then drift through the solar system, or even between star systems, until they eventually fall onto another world. If conditions there are suitable, the dormant life awakens and begins to spread. We know this process happens. Meteorites from Mars have been found on Earth, ejected from the red planet by ancient impacts and eventually captured by our gravity. Analysis of these rocks has revealed that some of them could have made the journey without being heated enough to sterilize any potential microbes. The reverse is also true. Earth rocks have been blasted into space, and some have likely reached Mars, Venus, and beyond. But panspermia suggests something more profound than just the exchange of microbes between neighbouring planets. It suggests that life might be a cosmic phenomenon, spreading from star system to star system over billions of years, carried on comets, asteroids, and interstellar dust. If this is true, then life on Earth might not have originated here at all. We might be the descendants of organisms that first emerged on a planet orbiting a star that died billions of years ago in a region of the galaxy we'll never be able to identify. Imagine that ancient world. Perhaps it orbited a red dwarf star, smaller and cooler than our Sun, but far longer lived. Red dwarfs can burn for trillions of years, providing stable conditions for life to evolve over timescales that dwarf Earth's entire history. On such a world, life might have had billions of years to develop, to experiment, to become something we can't even conceptualize. And then, perhaps, a catastrophe, a nearby supernova, a rogue planet disrupting the system, or simply the gradual cooling of the planet's core, brought that chapter to an end. But life, tenacious and adaptable, didn't end with the world that birthed it. Fragments of that planet carrying dormant microbes were scattered into space. They drifted through the darkness for millions of years, crossing the vast distances between stars until some of them fell onto younger worlds where conditions were just beginning to become suitable for life. And there, the cycle began again. If this happened once, why not many times? Why not a continuous process, stretching back to the earliest epochs of the universe, with life spreading like seeds on the wind, taking root wherever it finds fertile ground? In this vision, Earth is not the origin point of life, but merely one garden in an endless network of gardens, all connected by invisible threads of cosmic migration. The implications are staggering. It would mean that the life we see around us, the bacteria in the soil, the trees reaching toward the sky, the animals that walk and swim and fly, and yes, even us, all carry within them a heritage that predates our planet. We would be the inheritors of a story that began not here, but somewhere else, in a time so remote that even the stars that witnessed it have long since faded. And it would mean that we're not alone in the universe, not in the sense of encountering other intelligent civilizations, but in a deeper, more fundamental way. We would be part of a living cosmos, a universe where life is not a rare accident but a persistent pattern, endlessly repeating, endlessly adapting, endlessly reaching toward new possibilities. But let's push the question even further. Let's ask not just whether life existed a billion years ago, somewhere in the universe, but whether it might have existed here, on Earth, in forms and epochs that have been completely erased from the geological record. This is where the story becomes truly eerie, because it forces us to confront the limits of what we can know about the past. The rock record, as comprehensive as it seems, is full of gaps. Entire periods of Earth's history have been lost to erosion, subduction, and metamorphism. The oldest rocks we've found are about 4 billion years old, but Earth itself is 4.5 billion years old. That missing 500 million years, the Hadean Eon, is almost completely unknown to us. We have only a handful of tiny zircon crystals from that time, and they tell us tantalizingly little. What was Earth like during the Hadean? The name itself suggests a hellish landscape, and for a long time scientists assumed it was uninhabitable. A molten surface bombarded by asteroids, with no stable crust and no liquid water. But recent evidence has challenged that picture. Those ancient zircon crystals contain chemical signatures that suggest the presence of liquid water and possibly even continental crust. Some researchers now believe that Earth might have been habitable much earlier than we thought, perhaps within a few 100 million years of its formation. If that's true, then life could have emerged during the Hadean, and if it did, it would have faced a world utterly unlike anything that came after. The moon was closer, creating massive tides. The day was only a few hours long. The atmosphere was thick with carbon dioxide and water vapour. Volcanic activity was constant, reshaping the surface in ways we can barely imagine. Life in such a world would have been simple, microbial, clinging to whatever stable niches it could find. But here's the unsettling part. If life did emerge during the Hadean, we might never find evidence of it. The late heavy bombardment, a period around 4 billion years ago, when the inner solar system was pummeled by a surge of asteroid impacts, would have sterilized the surface, vaporizing oceans and melting the crust. Any life that existed before that cataclysm would have been wiped out, its traces erased so completely that not even fossils would remain. Unless, of course, some of it survived. Deep beneath the surface, in cracks and fissures where water circulated through hot rock, microbes might have endured. And when the bombardment ended and the surface became habitable again, they could have re-emerged, recolonizing a world that had been reset to zero. In this scenario, the life we see today might not be the first life on Earth, but the second, or even the third. We might be living in a world that has been wiped clean and reborn multiple times, with each iteration leaving no memory of what came before. The idea is speculative, but it's grounded in what we know about Earth's violent early history and the resilience of microbial life. And it raises a profound question. If life can be erased so completely that even the rocks forget it existed, how can we ever be certain about the true timeline of life's origins? There's another layer to this mystery, one that takes us beyond the purely scientific and into the realm of myth and collective memory. Across cultures and continents, separated by oceans and millennia, human beings have told stories about the origins of life and the world. And while these stories differ in their details, certain themes appear again and again with striking consistency. Many ancient myths describe a time before time, a primordial chaos from which order gradually emerged. The Babylonian Enuma Elish speaks of Tiamat, the saltwater ocean, and Apsu, the freshwater abyss, whose mingling gave birth to the first gods. The Hindu Rig Veda describes the cosmic ocean and the golden egg from which the universe hatched. The Chinese creation myths tell of Pangu, who separated the heavens from the earth, bringing form to formlessness. Other myths speak of life descending from the heavens. The Dogon people of Mali have traditions about beings from the star Sirius who brought knowledge and civilization. Greek mythology is filled with gods who came down from Olympus to shape the mortal world. Indigenous Australian stories describe the dream time when ancestral beings walked the earth and created the landscape and all living things. Are these myths simply imaginative attempts to explain the unknown? Or could they contain echoes of something deeper? Could they be humanity's way of remembering, in symbolic form, truths about our origins that are too ancient to be preserved in any other way? Consider the possibility that myths are not just stories, but compressed histories, metaphors that encode real events in language that can survive across countless generations. The flood myths that appear in cultures around the world might preserve memories of real catastrophic floods at the end of the last ice age. The stories of dragons and monsters might reflect encounters with megafauna or even dinosaur fossils. And the myths of life coming from the sky or emerging from primordial waters might be humanity's intuitive grasp of truths that science is only now beginning to articulate. If life did arrive on Earth from space, carried on comets or asteroids, then the image of gods descending from the heavens takes on new resonance. If life emerged from the oceans, as science tells us it did, then the myths of creation from water become not just poetry, but accurate description. And if life is far older than our planet, if it carries within it a heritage that stretches back to the earliest epochs of the universe, then perhaps the myths that speak of eternal cycles, of death and rebirth, of worlds that end and begin again, are touching on something profoundly true. This doesn't mean we should take myths literally, or abandon the rigorous methods of science in favour of ancient stories. But it does suggest that there might be wisdom in these old narratives, a kind of knowledge that operates on a different level than empirical observation. Myths speak to the part of us that senses patterns, that feels connections across time, that recognizes that we are part of something larger and older than ourselves. And when we ask whether life existed 1 billion years ago, whether it began before Earth, whether we are the inheritors of a story that predates our world, we're asking questions that myths have been exploring for as long as humans have been able to speak. Let's turn now to the cosmos itself, to the vast stage on which this drama of life's origins might have played out. When we look up at the night sky, we're looking backward in time. The light from distant stars takes years, centuries, even millions of years to reach us. The most distant galaxies we can observe are so far away that we're seeing them as they were billions of years ago, when the universe was young and our own galaxy hadn't even formed yet. This means that when we study the early universe, we're not just theorizing about what might have been, we're actually observing it, frozen in the light that has been travelling toward us across unimaginable distances. And what we see is a universe that was remarkably quick to develop the conditions necessary for life. Within the first billion years after the Big Bang, the universe had already cooled enough for atoms to form. Hydrogen and helium, the simplest elements, clumped together under gravity to form the first stars. These stars were massive and short-lived, burning through their fuel in just a few million years before exploding as supernovae. But in those explosions they created heavier elements, carbon, oxygen, nitrogen, iron, and scattered them into space. The debris from these first stars became the raw material for the next generation. Second-generation stars formed from clouds that were enriched with the elements necessary for rocky planets and, potentially, for life. By the time the universe was 1 billion years old, there were already planetary systems orbiting these stars, and some of those planets might have had liquid water, stable surfaces, and energy sources that could drive chemical evolution. We have no direct evidence of life from that era, and we likely never will. The distances are too vast, the timescales too remote. But the chemistry was there, the physics was there, the ingredients and the conditions were in place. And if life is, as we suspect, a natural consequence of chemistry under the right circumstances, then there's no reason to think it couldn't have begun. What would such early life have been like? It would have faced challenges we can barely imagine. The universe was more violent then, with more frequent supernova, more intense radiation, more chaotic planetary systems. But life, as we've learned from studying extremophiles on Earth, is extraordinarily adaptable. It finds ways to survive in boiling acid, in frozen wastelands, in the crushing pressures of the deep ocean, in solid rock miles beneath the surface. Given billions of years and an entire universe to work with, what might it have become? Perhaps it remained simple, microbial, spreading slowly from world to world through panspermia, but never developing the complexity we see on Earth. Or perhaps, on some worlds, it had time to evolve into forms we can't even conceptualize. Organisms adapted to environments so different from Earth that we wouldn't recognize them as alive. Life that metabolizes dark matter. Life that exists as patterns in plasma. Life that spans entire planets, thinking thoughts that take millennia to complete. These ideas sound like science fiction, but they're grounded in a simple recognition. Life on Earth represents only one solution to the problem of how to extract energy from the environment and maintain organization against entropy. There might be countless other solutions, and some of them might have been discovered billions of years before Earth even existed. There's a concept in cosmology called the habitable epoch of the universe, the period during which conditions are suitable for life as we understand it. According to current models, we're living in that epoch now. Stars are still forming, planets are still coalescing, and the universe is neither too hot nor too cold, neither too dense nor too diffuse, for life to emerge and thrive. But this epoch won't last forever. Trillions of years from now, the last stars will burn out. The universe will grow cold and dark, with matter spread so thin that no new stars can form. Eventually, even the longest-lived structures, black holes, will evaporate through Hawking radiation, leaving nothing but a thin soup of particles in an ever-expanding void. This is the heat death of the universe, the final equilibrium from which nothing can emerge. But before that end, there are trillions of years of possibility, and if life can persist, if it can adapt and spread and evolve across cosmic timescales, then the story we're part of might be only the beginning. Life that emerged 1 billion years after the Big Bang would now be 13 billion years old. If it survived, if it continued to evolve, what might it have become? This is where science gives way to speculation, but it's speculation grounded in what we know about evolution and adaptation. On Earth, life went from simple cells to complex multicellular organisms in about 3 billion years. It developed intelligence, technology, and the ability to leave its home planet in just a few million years after that. If life elsewhere had billions of additional years to evolve, it might have reached levels of complexity and capability that we can't even imagine. Perhaps it learned to manipulate matter at the atomic level, building structures and machines that seem like magic to us. Perhaps it developed ways to travel between stars, or even between galaxies, spreading across the universe like a living network. Perhaps it found ways to survive the death of stars, the collision of galaxies, even the eventual heat death of the universe itself. Or perhaps it simply continued to exist as it always had, simple, resilient, patient, waiting in the dark spaces between stars for the next opportunity to take root and begin again. The point is not to make definitive claims about what ancient life might have achieved, but to recognize that if life is as old as the universe's habitable epoch, then it has had time to become something far beyond what we see on Earth, and if that's true, then we might be living in a universe that is, in some sense, already alive. Not in the way we usually think of life, but as a vast interconnected system of which we are only the most recent and perhaps the most naive participants. Let's return to Earth for a moment, to the world we know, and ask what traces of ancient life we might still be able to find. If life existed on Earth during the Hadean, or if it arrived from elsewhere carrying a heritage billions of years old, would there be any way to detect it? The answer might lie not in rocks or fossils, but in the genetic code itself. Every living thing on Earth shares the same basic biochemistry, the same DNA structure, the same genetic code, the same fundamental cellular machinery. This suggests that all life on Earth descended from a single, common ancestor, an organism that lived billions of years ago and from which every subsequent species evolved. But here's the intriguing part. The genetic code we use is not the only possible code. There are millions of ways that DNA could be translated into proteins, and yet all life on Earth uses the same translation system. This universality suggests that the code was established very early, before life diversified, and has been preserved ever since because any change would be catastrophic. Some researchers have suggested that the genetic code might contain information about life's origins, not in the genes themselves, but in the structure of the code. Certain features of the code seem optimized in ways that are hard to explain by chance alone. It's resistant to errors, meaning that mutations are less likely to produce harmful changes. It's also structured in a way that allows for gradual evolution, with similar codons producing similar amino acids. Could this optimization be evidence of a very long evolutionary history, one that predates Earth? If life emerged elsewhere and evolved for billions of years before arriving here, it might have had time to refine its genetic code to a level of efficiency that seems almost designed. The code we carry in our cells might be an ancient inheritance, a message written in the language of chemistry that has been passed down through countless generations across unimaginable spans of time. There's another possibility, even more speculative but worth considering. Some scientists have proposed that certain features of the genetic code might actually encode information. Not genetic information in the usual sense, but something more like a signature or a timestamp. If an advanced civilization wanted to leave a message that would persist across cosmic timescales, embedding it in the genetic code of life itself would be one way to do it. The code is copied every time a cell divides, preserved across billions of generations, and present in every living thing. This idea, sometimes called the biological SETI hypothesis, suggests that we might find evidence of ancient intelligence not by listening for radio signals from space, but by looking more carefully at the code we carry within us. It's a fringe idea, and most scientists are skeptical, but it points to a deeper truth. The genetic code is a historical document, a record of life's journey through time, and we're only beginning to learn how to read it. As we drift deeper into this mystery, we need to consider the philosophical implications of what we're exploring. If life is billions of years old, if it predates Earth, if it has been spreading through the cosmos for eons, then what does that mean for our understanding of ourselves and our place in the universe? One implication is humbling. We tend to think of humanity as the pinnacle of evolution, the most advanced form of life, the species that has finally achieved consciousness and the ability to understand the universe. But if life is as old as we're suggesting, then we're not the pinnacle, we're barely the beginning. We're infants in a story that has been unfolding for billions of years, and whatever wisdom or capability we've achieved is nothing compared to what might have come before. But there's another implication that's more hopeful. If life is that old, that persistent, that adaptable, then it suggests that life is not fragile but resilient. It survives catastrophes, it endures extinctions, it finds ways to persist even when entire worlds are destroyed. And if that's true, then perhaps we don't need to fear so much for the future. Life will continue in some form long after we're gone. The story we're part of is larger than any individual species, any single planet, any particular moment in time. There's also a spiritual dimension to this question, though it's one that science can't directly address. Many people find meaning in the idea that we're connected to something larger than ourselves, to nature, to the cosmos, to the divine. If life is billions of years old, if we carry within us a heritage that stretches back to the earliest epochs of the universe, then that connection becomes literal. We're made of stardust, as Carl Sagan famously said, but we might also be made of something even more profound. The accumulated wisdom of billions of years of evolution, the persistence of a pattern that has been learning and adapting since the universe was young. This doesn't require belief in any particular religion or philosophy. It's simply a recognition that we are part of a continuum, a living thread that connects the present to the deepest past and the furthest future. And in that recognition, there might be a kind of peace, a sense that our individual lives, as brief and fragile as they are part of something enduring and meaningful. Let's explore one more possibility before we begin to draw this journey to a close. What if life didn't just exist a billion years ago, but has existed in multiple forms, in multiple epochs, in ways that we're only now beginning to suspect? There's a concept in astrobiology called a shadow biosphere, the idea that there might be forms of life on Earth that are so different from the life we know that we haven't recognized them as alive. These wouldn't be aliens from space, but organisms that evolved separately from the rest of life. using different biochemistry, different genetic codes, different metabolic pathways. The idea emerged from the recognition that our methods for detecting life are biased toward the kind of life we're familiar with. We look for DNA, for proteins, for cells with membranes. But what if there are organisms that don't use DNA? What if there are forms of life based on different chemistry entirely? Silicon instead of carbon, ammonia instead of water, or something even more exotic? If such organisms exist, they might be all around us, invisible because we don't know how to look for them. They might live in extreme environments where conventional life can't survive, or they might exist in the same environments as familiar life, but occupy different ecological niches. They might be slow-growing, or microscopic, or so different in their structure that we mistake them for non-living chemical processes. Now extend this idea backward in time. If a shadow biosphere exists today, could there have been shadow biospheres in the past? Could there have been forms of life on Earth that rose and fell, leaving no trace because they were so different from what came after that even their fossils wouldn't be recognizable? Imagine an early Earth populated by organisms that used a completely different genetic system, one that was eventually outcompeted by DNA-based life and went extinct. Or imagine life that existed during the Hadean, adapted to the extreme conditions of that time, but unable to survive when the environment changed. These lost biospheres would be invisible to us now, erased not just by geological processes, but by the simple fact that we wouldn't know what to look for. The idea is speculative, but it highlights how much we still don't know about life's history. Every discovery in paleontology, every new fossil, every ancient rock formation analysed, reveals that life is more diverse, more adaptable, and more ancient than we previously thought. And each revelation suggests that there might be even more to discover, even deeper layers of history waiting to be uncovered. As we approach the end of this journey, let's return to the question we started with. What if 1 billion years ago, life had already begun? We've explored the scientific evidence, the timeline of Earth's formation, the emergence of life in the fossil record, the chemistry of the early universe. We've considered the possibility of panspermia, the idea that life might have spread from world to world across cosmic distances. We've looked at the gaps in the geological record, the lost epochs that might have harboured forms of life we can never recover. We've touched on myths and stories, the ways that human cultures have intuited truths about origins that science is only now beginning to articulate. And we've speculated about shadow biospheres, ancient genetic codes, and the possibility that life is far older and more persistent than we ever imagined. What emerges from all of this is not a definitive answer, but a deepening of the mystery. The more we learn about life, the more we realize how little we truly understand about its origins and its nature. Every answer leads to new questions. Every discovery reveals new horizons. But perhaps that's as it should be. Perhaps the point is not to solve the mystery, but to live within it, to recognize that we are part of a story that began long before us and will continue long after we're gone. A story written in the language of chemistry and physics, but also in the language of myth and meaning. A story that connects us to the deepest past and the furthest future, to the smallest microbe and the largest galaxy. If life did begin 1 billion years ago, or even earlier, then we are the inheritors of an unimaginably ancient heritage. The atoms in our bodies were forged in stars that died before our sun was born. The genetic code in our cells might carry information that predates our planet. The very fact of our existence might be the result of processes that have been unfolding for billions of years across distances we can barely comprehend. And yet, here we are, conscious, aware, able to ask these questions and to wonder about our place in the cosmos. That alone is remarkable. That alone is worth contemplating as you drift towards sleep. Picture, if you will, an ancient ocean, not Earth's ocean, but one that existed long before our world took shape. It laps against shores of black rock under a sky filled with unfamiliar stars. The water is warm, heated by volcanic vents below and a young sun above. And in that water, something is stirring. It's not complex. It's barely alive by any definition we would recognize. Just a few molecules that have learned to copy themselves, to extract energy from their surroundings, to persist against the natural tendency of the universe toward disorder. But it's enough. It's the beginning. Millions of years pass. The simple replicators become more complex. They develop membranes to separate themselves from the environment. They learn to metabolize different chemicals to adapt to changing conditions. Some of them are swept up in asteroid impacts, blasted into space, frozen in the void. They drift for eons, dormant but not dead, waiting. Eventually, some of them fall onto a new world, a young planet still cooling from its formation, with oceans beginning to form and a thick atmosphere of carbon dioxide and water vapor. The dormant microbes awaken. They find the conditions suitable. They begin to reproduce, to spread, to evolve. Billions of years pass. The simple microbes become more complex. They learn to photosynthesize, to breathe oxygen, to form multicellular structures. They survive extinctions, ice ages, asteroid impacts. They adapt to every environment the planet offers: hot springs, frozen tundra, deep ocean trenches, solid rock miles beneath the surface. And eventually, after billions of years of evolution, they become us, conscious beings, capable of looking up at the stars and wondering where we came from, capable of asking whether life began here or somewhere else, or everywhere at once. The ocean we imagined at the beginning might have been on Earth, or it might have been on a world that no longer exists, orbiting a star that has long since died. It doesn't matter. The pattern persists, the story continues, and we are part of it, carrying forward a heritage that might be as old as the universe itself. As you close your eyes tonight, let yourself feel that connection. You're not separate from the cosmos, but woven into it. The same forces that shaped the first stars are still at work in your body. The same chemistry that sparked life billions of years ago is still unfolding in every cell. You are ancient and you are new, a momentary expression of something eternal. The question of whether life began 1 billion years ago, or 10 billion years ago, or yesterday, becomes less important than the recognition that life is here now, and that you are part of it. You are a wave in an ocean that has been flowing since the beginning of time. You're a note in a song that has been playing since the first stars ignited. You're a thought in a mind that might be as vast as the universe itself. And perhaps that's the deepest truth we can touch, that life is not something that happens in the universe, but something the universe does. It's not an accident or an anomaly, but a fundamental expression of what matter becomes when given enough time and the right conditions. It's the universe waking up, becoming aware of itself, asking questions about its own origins. So rest now, knowing that you are part of something larger than you can imagine. The story that began billions of years ago continues in you and will continue long after you're gone. The spark that first ignited in some ancient ocean on some distant world under some forgotten sky, still burns. It burns in the stars above. It burns in the earth below. And it burns in you, right now, in this moment. Sleep well, traveller. The universe is vast and the night is long, but you are not alone. You never were. You are part of the oldest story ever told, and the story is still being written. Consider for a moment the nature of memory itself. You remember yesterday, perhaps last week, maybe fragments from your childhood, but the atoms in your body remember further back. The carbon in your bones was forged in a star that died before the sun was born. The iron in your blood was created in a supernova explosion that lit up a corner of the galaxy when the universe was young. Your body is made of memories that predate memory itself. Now extend that thought. If those atoms carry the history of stellar death and rebirth, what else might they carry? What if the very building blocks of your cells once formed part of something alive on a world that no longer exists? What if the molecules that make you possible have been part of the machinery of life not once, but many times, across billions of years? This is not mysticism. This is chemistry, physics, the simple truth of how matter moves through the cosmos. Nothing is ever truly new. Everything is recycled, reformed, repurposed. The universe is endlessly creative, but it works with the same materials over and over again. And if life is one of the things the universe does with those materials, then perhaps life itself is far older than we've dared to imagine. Perhaps you're not just related to ancient life. Perhaps you are ancient life continuing. Let's imagine a specific scenario, grounded in what we know about the early universe. About 10 billion years ago, when the cosmos was roughly a quarter of its current age, the first generation of stars had already lived and died. The second and third generations were burning bright, and around some of them planets were forming. These weren't planets like Earth. Not yet. The universe was still learning how to make worlds, but some of those planets had water. We know this because the ingredients for water, hydrogen and oxygen, were abundant even then. Some had atmospheres, some had the right temperature, the right chemistry, the right energy sources, and on at least one of them, in an ocean or a hydrothermal vent or a warm little pond, something happened. Molecules began to organize themselves. Perhaps it started with simple self-replicating chains, RNA-like structures that could copy themselves imperfectly, creating variation, creating the raw material for evolution. Perhaps it happened quickly, or perhaps it took hundreds of millions of years. But eventually, on that ancient world, life emerged. What would it have been like? Almost certainly microbial at first. Single cells, or perhaps something even simpler. Something we wouldn't quite recognize as cellular. But it would have had the essential quality, the ability to maintain itself, to reproduce, to evolve. And once that threshold was crossed, everything changed. Because life, once it begins, is remarkably persistent. It finds ways to survive. It adapts. It spreads. Think about the timescales involved. If life emerged on a planet 10 billion years ago, it would have had roughly 6 billion years to evolve before Earth even existed. 6 billion years. For context, life on Earth went from single cells to human civilization in less than 4 billion years. What could 6 billion years produce? The possibilities are staggering. Perhaps that ancient life remained simple, never developing beyond microbial mats and simple colonies. Perhaps the conditions on that world weren't quite right for complexity to emerge. Perhaps it was a dead end. A brief experiment that ended when the planet's star expanded or its atmosphere was stripped away by stellar winds. Or perhaps it thrived? Perhaps it developed photosynthesis, or something like it. Perhaps it learned to harness chemical energy in ways we haven't discovered. Perhaps it built structures, ecosystems, webs of interaction and interdependence. Perhaps, given enough time, it became complex, multicellular, differentiated, intelligent. We have no evidence for this, of course, but we have no evidence against it either. The universe is vast and time erases almost everything. A civilization that rose and fell 8 billion years ago would leave no trace we could detect from here. Their planets might have been consumed by their dying stars or sterilized by cosmic catastrophes, or simply recycled into new generations of worlds. The universe forgets, but matter remembers in its way. And if some of that ancient life was cast into space, preserved in the cold and dark, then perhaps it's still out there. Perhaps some of it is here. There's a particular kind of vertigo that comes from contemplating deep time. We're used to thinking of history in terms of centuries, maybe millennia. The rise and fall of civilizations, the great events that shaped human culture. But those timescales are nothing compared to geological time, and geological time is nothing compared to cosmic time. 4 billion years ago, Earth was a hellish place, bombarded by asteroids, its surface molten or barely solid. But it was already ancient by human standards, older than the oldest mountains we know today, older than any rock we've ever found. And yet, in cosmic terms, it was brand new, a baby world just beginning its story. Now imagine looking back twice that far, 8 billion years ago. The universe was half its current age, but it was already mature, already full of stars and planets and the complex chemistry that makes life possible. Entire epochs of cosmic history had already passed. Stars had been born, lived, and died. Galaxies had collided and merged, and somewhere, perhaps, life had already been thriving for billions of years. The human mind isn't built to grasp these timescales. We try to use metaphors. If the history of the universe were a calendar year, humans appeared in the last few seconds before midnight. But even those don't quite capture the reality. The universe is old, unimaginably old. And if life is even a fraction as old as the universe itself, then we are not the pioneers we imagine ourselves to be. We are latecomers, arriving at a party that's been going on for eons. Let's return to the mechanism, to panspermia, because it's central to understanding how ancient life could have spread. When we think of life travelling between worlds, we might imagine it as a rare, unlikely event. But the universe is constantly exchanging material between its parts. Every time a large asteroid or comet strikes a planet with enough force, it ejects material into space. Some of that material escapes the planet's gravity entirely and begins a journey through the cosmos. If the planet harbours life, some of that life might be carried along, embedded in rocks, protected from radiation by layers of stone. We know this happens because we've found meteorites from Mars on Earth. We've found meteorites from the Moon. We've even found meteorites that might have come from Vesta, a large asteroid. If rocks can travel between worlds in our solar system, they can travel between star systems too. It just takes longer, much longer. A rock ejected from a planet might drift through space for millions of years before encountering another world. But millions of years is nothing to a dormant microbe. Frozen in the cold of space, its metabolism shut down completely. Some Earth bacteria can survive in that state for extraordinary periods, and if life is truly ancient, if it's been spreading through the galaxy for billions of years, then time is not a constraint. It's an opportunity. Picture it. A vast, slow-motion dispersal, life spreading from world to world like seeds on the wind, taking root wherever conditions allow, lying dormant where they don't. Some lineages dying out, others persisting, adapting, evolving in new directions on new worlds. A cosmic web of life, connected not by communication or travel, but by deep ancestry, by the shared inheritance of that first spark. There's something both humbling and exhilarating about this possibility. Humbling because it means we are not special, not the first, not the pinnacle of anything. We are one branch on a tree that might have roots stretching back to the beginning of time itself. But exhilarating because it means we are part of something vast, something that transcends any individual world or species or moment. You're not just a human being, living on Earth in the 21st century. You're a temporary configuration of matter that has been alive, in one form or another, for billions of years. The molecules in your cells have been part of countless organisms on countless worlds under countless skies. You are a continuation, not a beginning. And when you die, those molecules will continue. They'll return to the earth, or be scattered to the wind, and eventually they'll become part of something else. Another organism, another form of life. The pattern that is you will dissolve, but the matter that makes you possible will persist, will be recycled, will perhaps one day leave Earth entirely and seed life on some distant world. You're not separate from the cosmos. You're the cosmos, experiencing itself, knowing itself, wondering about itself. Let's explore what ancient complex life might have been like, if it existed. This is pure speculation, of course, but it's speculation grounded in what we know about how evolution works and what's possible within the laws of physics and chemistry. If life emerged 10 billion years ago, and had 6 billion years to evolve before Earth formed, it could have developed complexity we can barely imagine. On Earth, the jump from single cells to multicellular organisms took billions of years, but once it happened, evolution accelerated. Within a few 100 million years, we had the Cambrian explosion, an extraordinary diversification of body plans and ecological strategies. Now imagine that process continuing for billions of years more. What forms might life take? What senses might it develop? What ways of interacting with its environment? Perhaps there were organisms that could perceive magnetic fields directly, navigating by the lines of force that thread through space. Perhaps there were creatures that communicated through quantum entanglement, their thoughts linked across distances in ways that seem impossible to us. Perhaps there were ecosystems that spanned entire planets, single organisms so vast and distributed that they were effectively immortal, their consciousness, if they had consciousness, operating on timescales of millions of years. Or perhaps they were nothing like that. Perhaps they were utterly alien, based on chemistry we haven't considered, perceiving reality in ways we can't imagine. Perhaps they would look at us and not recognize us as alive at all, just as we might look at them and see only interesting geology. There's a concept in astrobiology called the shadow biosphere. The idea that there might be life on Earth that we haven't detected because it's so different from the life we know that we don't recognize it. It might use different amino acids, different nucleotides, different fundamental chemistry. It might be all around us, invisible, because we're not looking for it in the right way. Now extend that concept across the cosmos and across time. If life has been emerging independently on different worlds for billions of years, there might be dozens or hundreds or thousands of different kinds of life, each with its own biochemistry, its own solutions to the problems of metabolism and reproduction and evolution. Some of that life might be based on carbon and water, like us, but some might use silicon instead of carbon, or ammonia instead of water. Some might thrive in conditions we consider impossibly hostile, in the clouds of gas giants, or in the cold methane lakes of distant moons, or in the interiors of asteroids, or in the accretion disks around black holes. And if that life is ancient, if it's been evolving for billions of years longer than life on Earth, it might have spread far beyond its world of origin. It might have adapted to survive in space itself, in the thin gas between stars, or in the even thinner gas between galaxies. It might be everywhere, and we simply don't know how to see it. This isn't science fiction. This is a serious possibility that some astrobiologists consider. The universe is stranger than we imagine, and it might be stranger than we can imagine. Let's think about what traces ancient life might leave, and why we might never find them. On Earth, the oldest fossils we've found are about 3.5 billion years old, and they're controversial. Some scientists argue they're not biological at all, just interesting mineral formations. The older you go, the harder it is to find evidence of life, because geological processes erase almost everything. Rocks get subducted into the mantle, melted, reformed. Continents collide and mountains rise and erode. The surface of the Earth is constantly being recycled. Very little survives from the deep past, and what does survive is often ambiguous, open to interpretation. Now imagine trying to find evidence of life that existed not on Earth, but on some other world, billions of years ago. That world might not even exist anymore. It might have been consumed when its star became a red giant, or shattered by a collision, or sterilized by a nearby supernova. Even if the planet still exists, its surface has been reworked countless times. Any fossils, any chemical signatures, any structures built by ancient organisms, all of it would be gone, erased by time and geology and cosmic catastrophe. The universe is not a museum. It doesn't preserve things for our convenience. It's a dynamic, violent, creative place, constantly destroying and rebuilding. The past is not stored somewhere waiting to be discovered. The past is gone, and only the faintest echoes remain. And yet, we keep looking. We keep asking questions. Because even if we can never prove that ancient life existed, the possibility itself changes how we think about our place in the cosmos. There's a particular poignancy to the idea that we might be surrounded by the descendants of ancient life and not know it. Every time you touch soil, you're touching billions of microorganisms, each one a marvel of complexity, each one the product of billions of years of evolution. But how much of that evolution happened on Earth, and how much happened elsewhere? Some of those microbes might carry genes that originated on another world, in another ocean, under another sun. They might be the distant descendants of organisms that travelled through space, that survived the cold and the radiation and the loneliness of the void, that landed here and adapted and thrived, and became part of Earth's biosphere. We wouldn't know. The genetic code would look the same. DNA is DNA, after all. The chemistry would be familiar. But the history, the deep ancestry, might stretch back not just to Earth's formation, but to a time before Earth existed, to a place we'll never be able to identify. This is the cosmic amnesia we live with. We are children of the universe, but we don't remember our birth. We don't know where we came from, not really. We have theories, evidence, educated guesses, but the truth is lost in deep time, beyond the reach of any fossil record, any geological layer, any measurement we can make, and perhaps that's okay. Perhaps the mystery is part of what makes the question beautiful. Let's imagine you could somehow perceive deep time directly, could see the full history of the matter that makes up your body. You would see atoms forged in stellar cores, scattered by supernovae, drifting through space for millions of years. You would see them condensing into new stars, new planets, new worlds. You would see them becoming part of rocks, oceans, atmospheres, and then, perhaps, you would see them becoming part of something alive. A simple cell, dividing and dividing, evolving, adapting. You would see that lineage branch and diversify, some branches dying out, others persisting. You would see those organisms spreading, perhaps being carried into space, drifting, landing on new worlds, beginning again. You would see the atoms in your body passing through countless forms, countless lives, across billions of years and countless light years of space. You would see them as part of a vast interconnected web of existence, a web that spans the cosmos and stretches back to the beginning of time. And finally, you would see them coming together to form you. This particular configuration, this particular pattern, this particular moment of consciousness and awareness. You would see yourself not as a separate thing, but as a temporary expression of something eternal, something that has been flowing and changing and evolving since the first stars ignited. This is not a metaphor. This is literally true. You're made of stardust, yes, but you might also be made of ancient life, of organisms that lived and died on worlds that no longer exist, of a story that began long before Earth was born. There's a question that haunts anyone who thinks deeply about these possibilities. If life is ancient, if it's been spreading through the cosmos for billions of years, why haven't we found it? Why haven't we detected signals from ancient civilizations, or encountered their artifacts, or seen evidence of their engineering projects? This is the Fermi paradox, and it has many possible answers. Perhaps intelligent life is rare, even if simple life is common. Perhaps civilizations destroy themselves before they can spread to the stars. Perhaps they're out there, but we're not looking in the right way, or they're not interested in communicating with us, or the distances are simply too vast for contact to be practical. Or perhaps the answer is simpler and more profound. Perhaps we are the ancient life. Perhaps the story we've been imagining, life emerging billions of years ago, spreading through the cosmos, seeding world after world, is our story. Perhaps we're the descendants of that first spark, and we simply don't remember because the journey was too long, the changes too profound, the evidence too thoroughly erased by time. Perhaps Earth is not the origin of life, but one of countless way stations in a journey that began when the universe was young. Perhaps we are not waiting to find ancient life. Perhaps we are ancient life, continuing its endless exploration of what's possible. As you lie here, breathing slowly, feeling the weight of your body against the surface beneath you, consider the journey that brought you to this moment. Not just your personal journey, your birth, your childhood, your life, but the deeper journey, the one that spans billions of years. The oxygen you're breathing was produced by photosynthetic organisms, descendants of bacteria that learned to harness sunlight billions of years ago. But where did those bacteria come from? Did they evolve on Earth, or were they seeded here by material from space? Did their ancestors live on another world, under another sky? The water in your cells, the water that makes up most of your body, is ancient. Some of it might be older than the solar system, formed in the molecular clouds between stars. That water has been part of comets and asteroids, has fallen as rain on countless worlds, has been part of countless organisms. It carries within it the memory of deep time, of journeys across the cosmos, of transformations we can barely imagine. And the carbon, the element that forms the backbone of every molecule in your body, was forged in the heart of a dying star. That star lived and died before the sun was born. Its death was violent, spectacular, a supernova that briefly outshone an entire galaxy. And from that death came the raw materials for new life, new worlds, new possibilities. You are made of endings and beginnings. You are made of death and rebirth. You are made of matter that has been cycling through the cosmos for billions of years, taking countless forms, part of countless stories. There's a meditation practice in some traditions where you contemplate the interconnectedness of all things, tracing the web of causes and conditions that brought you into existence. You think about your parents, your grandparents, your ancestors stretching back through time. You think about the food you ate today, and the sun that grew that food, and the soil that nourished it. You think about the water you drank, and the rain that fell, and the ocean that evaporated to form that rain. Now extend that meditation across cosmic time. Think about the stars that died to create the elements in your body. Think about the planets that formed and dissolved and reformed. Think about the possibility, the real, scientific possibility, that some of the matter in your body was once part of living organisms on other worlds, in other eras, under other skies. You're not separate from the cosmos. You're not a visitor here, not an accident, not an anomaly. You're what the universe does. You're what matter becomes when given enough time and the right conditions. You're the universe becoming aware of itself, asking questions about its own nature, marveling at its own existence. And if life is truly ancient, if it's been part of the cosmos for billions of years, then consciousness might be ancient too. The awareness you feel right now, the sense of being present, of experiencing this moment, that might not be a recent development, a quirk of evolution on one particular planet. It might be something fundamental, something that emerges whenever matter organizes itself in certain ways, something that's been happening over and over again across the cosmos for billions of years. You might not be the first consciousness to wonder about these questions. You might be one of countless minds across countless worlds and countless eras, all asking the same fundamental questions. Where did I come from? What am I? Why am I here? Let's imagine one more scenario, one more possibility to carry with you as you drift towards sleep. Imagine that life did begin 10 billion years ago, on a world we'll never know, in a solar system that no longer exists. Imagine that it evolved, slowly at first, then faster, developing complexity and diversity and eventually intelligence. Imagine that those ancient beings looked up at their sky and wondered, just as we do, whether they were alone. Imagine that they developed science, technology, philosophy. Imagine that they asked the same questions we're asking now. How did life begin? Are we the first? What came before? And imagine that they never found the answers. Imagine that they searched their world for evidence of earlier life, earlier civilizations, and found nothing. Imagine that they concluded, as we have, that they were the first, the pioneers, the beginning of the story. But they were wrong. They weren't the first. There had been others before them, on other worlds, in other eras. But time had erased all evidence. The universe had forgotten. And then imagine that those beings, like all beings, eventually passed away. Their civilization ended, their world was destroyed or transformed, and the universe moved on. But some of their microbes, some of their simplest organisms survived. They were carried into space, they drifted for millions of years, and eventually they landed on new worlds. They adapted, they evolved, they became the ancestors of new forms of life. Perhaps they became the ancestors of life on Earth. Perhaps you are their descendant, carrying within you the genetic legacy of beings who lived and died billions of years ago, who asked the same questions you're asking now, who wondered about their place in the cosmos just as you do. And perhaps, billions of years from now, when Earth is gone and humanity is a distant memory, some of your descendants, microbes perhaps, or something more complex, will seed life on another world. And beings on that world will look up at their sky and wonder if they're alone, never knowing that they carry within them the legacy of Earth, of humanity, of you. The story continues. It always continues. Life is not a moment, not an event, but a process, a flow, a river that's been running since the beginning of time and will run until the end. As you close your eyes now, let yourself feel the weight of deep time, the vastness of the cosmos, the extraordinary improbability and yet the apparent inevitability of your existence. You are here, now, aware, alive. You are part of a story that might be as old as the universe itself, a story that will continue long after you're gone. The atoms in your body have been on a journey for billions of years. They've been part of stars and planets, rocks and oceans, countless organisms across countless worlds. They've travelled distances you can't imagine, survived conditions that would seem impossible, and somehow, against all odds, they've come together to form you. This moment, this breath, this awareness, it's all part of that ancient journey. You're not separate from it. You are it. You are the universe experiencing itself, knowing itself, wondering about itself. And when you wake tomorrow, those atoms will still be on their journey. They'll continue to be part of you for a while longer, and then they'll move on, becoming part of something else, continuing the endless cycle of transformation and renewal. But for now, rest. Let the questions fade. Let the wonder remain, but let it be a peaceful wonder, a gentle awe. You're part of something vast and ancient and beautiful, something that transcends understanding, something that simply is. The universe is old, and you are young, but you are made of the universe, and in that sense you are as old as time itself. You are ancient and new, temporary and eternal, a single note in an endless song. Sleep now, knowing that you are exactly where you're supposed to be, exactly when you're supposed to be here. The story that began billions of years ago continues in you, and that is enough. That is everything. The stars are still burning, the cosmos is still expanding, life is still spreading, still evolving, still reaching toward new possibilities, and you are part of it all, now and always, a wave in an ocean that has no beginning and no end. Rest well, ancient traveller. The journey continues, but for now, be still, be present, be at peace. But before you drift completely into sleep, consider one more mystery, one that touches the very foundation of what life is and why it exists at all. The universe, left to its own devices, tends toward disorder. This is one of the most fundamental laws of physics. Entropy always increases. Hot things cool down. Organized things fall apart. Mountains erode. Stars burn out. Everything, given enough time, dissolves into uniform, featureless equilibrium. And yet, here you are, impossibly organized, impossibly complex, a system of such intricate order that it can contemplate its own existence. Life is the universe's rebellion against its own tendency toward chaos, or perhaps And this is the more beautiful thought. Life is the universe's way of creating islands of order, temporary but exquisite, before the final dissolution. Think about what you're doing right now, in this very moment. You're breathing. Your heart is beating. Your cells are manufacturing proteins, repairing damage, converting nutrients into energy. You are a furnace of controlled chemical reactions, a cascade of precisely orchestrated molecular events. You are managing energy flows, taking in order from your environment, food, oxygen, sunlight captured by plants, and using it to maintain your own internal organization. And in the process, yes, you're creating waste heat, increasing the entropy of your surroundings, but locally, temporarily, you are a pocket of increasing order in a universe trending toward disorder. This is what life does. This is what life is. A dissipative structure, as some scientists call it. A pattern that maintains itself by channeling energy, by creating order here at the cost of disorder there. And if life is ancient, if it emerged billions of years before Earth, then this process, this beautiful, defiant process of creating order from chaos, has been happening for most of the universe's history. Imagine those first living systems, whatever they were, wherever they emerged. They would have been doing the same thing you're doing now, managing energy gradients, maintaining boundaries between inside and outside, preserving patterns against the relentless tide of entropy. Perhaps they were simpler than you, almost certainly they were, but the fundamental principle was the same. They were systems that could harness energy flows to maintain and replicate their own organization. And once that process began, once the universe discovered this trick of creating local order, it never stopped. The pattern spread, it diversified, it became more sophisticated. But the core principle remained unchanged across billions of years. There's something profound in this. Life isn't separate from the laws of physics. Life is what happens when the laws of physics are applied to systems with the right properties in the right conditions. You are not violating the second law of thermodynamics. You are fulfilling it, in a sense. You are part of the universe's exploration of all the ways that energy can flow, all the patterns that can emerge, all the temporary structures that can exist before everything finally runs down. And if ancient life existed, it was doing the same thing, creating order, managing energy, maintaining patterns for billions of years across countless worlds in conditions we can barely imagine. The universe has been practicing this art for a very long time. Let's think about information now, because life is not just about energy. It's about information. Your DNA contains instructions, patterns preserved across generations. The sequence of base pairs in your genome is information, pure and simple. Information about how to build proteins, how to regulate cellular processes, how to construct something as complex as you. And that information is ancient. Some of the genes you carry are essentially unchanged from versions that existed in single-celled organisms billions of years ago. The information has been copied, transmitted, preserved across unimaginable spans of time. Information, unlike matter and energy, can be perfectly preserved. The same pattern can exist in different substrates, can be copied without loss, can persist even as the physical medium changes. If life is truly ancient, if it predates Earth by billions of years, then some of the information in living systems might be older than we can comprehend. Think about that. The instructions for certain fundamental cellular processes, how to replicate DNA, how to synthesize proteins, how to generate energy from chemical gradients, These might be patterns that have been preserved and transmitted for 10 billion years or more. The information doesn't care what molecules it's encoded in. As long as those molecules can preserve and transmit the pattern, it could have started in one chemistry, been translated into another, spread across the galaxy, adapted to new conditions. But the core information, the essential instructions, might remain. You might be carrying information that is older than the sun, patterns that have been preserved through countless generations across countless worlds, through catastrophes and migrations and transformations we can't even imagine. There's a kind of immortality in this. Not the immortality of any individual organism, but the immortality of patterns, of information, of the instructions for creating order from chaos. Individual organisms die, planets are destroyed, stars burn out, but the information can persist, can be copied to new substrates, can continue its journey through time. If ancient life existed, its legacy might not be in fossils or artifacts. Its legacy might be in the information itself, in the patterns that have been preserved and transmitted, that exist now in every living thing, including you. You're not just made of ancient atoms. You might be running ancient software, executing instructions that have been refined and preserved across cosmic time. Let's turn our attention to the extremophiles, the organisms on Earth that survive in conditions that seem utterly hostile to life. There are bacteria that live in boiling water, in acidic pools that would dissolve metal, in the crushing pressures of the deepest ocean trenches. There are organisms that can survive in the vacuum of space, that can withstand radiation levels that would be instantly fatal to humans, that can remain dormant for millions of years and then revive when conditions improve. Tardigrades, tiny, 8-legged creatures barely visible to the naked eye, can survive being frozen to near absolute zero, heated to well above the boiling point of water, exposed to radiation thousands of times stronger than what would kill a human. They can dry out completely, losing almost all their water and remain in suspended animation for decades. And then, when water returns, they simply rehydrate and continue living as if nothing happened. These organisms are not alien. They're here, on Earth, right now. They're our relatives, branches of the same tree of life that includes you. But they show us something important. They show us that life is far more resilient, far more adaptable, far more capable of surviving extreme conditions than we might have imagined. And if life on Earth can do this, if it can survive in boiling acid, in frozen wastelands, in the vacuum of space, then what might ancient life have been capable of? Perhaps those first organisms, emerging in the early universe, were extremophiles by necessity. Perhaps they had to be, because the conditions in the young cosmos were so different from what we experience now. Imagine life that evolved in the accretion disk of a young star, where temperatures fluctuate wildly and radiation is intense. Imagine organisms that could survive being frozen in interstellar space for millions of years, then revive when they encountered a new world. Imagine systems that could extract energy from radiation, from magnetic fields, from sources we haven't even considered. The extremophiles on Earth might be echoes of that ancient adaptability. They might be carrying strategies, encoded in their genes, that were developed billions of years ago in conditions very different from modern Earth. When you look at a tardigrade surviving in the vacuum of space, you might be looking at a capability that was essential for ancient life spreading through the cosmos. When you see bacteria thriving in boiling water, you might be seeing a solution that was discovered long before Earth existed. These organisms are windows into deep time. They show us that life is not fragile, not delicate. not confined to the narrow range of conditions we find comfortable. Life is robust. Life is persistent. Life finds ways. And if it finds ways here, on this one planet, in this brief moment of cosmic time, then it has surely found ways elsewhere, elsewhen, in conditions we can barely imagine. The extremophiles are not oddities. They might be the norm. We might be the oddities, organisms adapted to unusually stable, unusually gentle conditions. The extremophiles might be showing us what life really is, what it's always been, what it had to be to survive and spread through the harsh environment of the early universe. Now let's consider something even stranger, the nature of time itself. You experience time as a steady flow, a river carrying you from past to future. Seconds tick by at a constant rate, minutes accumulate into hours, hours into days, days into years. But time is not absolute. Einstein showed us that. Time flows at different rates, depending on how fast you're moving, how deep you are in a gravitational field. Time is relative, flexible, woven into the fabric of space itself. And for different organisms, time is experienced differently. A mayfly lives for a single day, but in that day it experiences a complete life: birth, growth, reproduction, death. To the mayfly, that day might feel as full and complete as your entire lifetime feels to you. A tree lives for centuries, growing slowly, responding to seasons, existing on a timescale that makes human lives seem like brief flickers. If ancient life existed, if it evolved over billions of years in conditions very different from Earth, how might it have experienced time? Perhaps there were organisms that lived for millions of years, individual entities that persisted across timescales we can barely comprehend. To such a being, the rise and fall of civilizations would be like the beating of a heart to you, regular rhythm barely noticed. Or perhaps there were systems that operated on timescales of microseconds, living entire lifetimes in the blink of an eye, experiencing subjective eons in what we would perceive as an instant. Time is not the same for all observers. And if life is ancient and diverse, then it has explored many different relationships with time, many different ways of existing in the flow of moments. There's a meditation in this. Your experience of time is not the only possible experience. The pace at which you live, the rhythm of your days, the span of your lifetime, these are not universal constants. They're specific to your biology, your scale, your particular way of being alive. Ancient life might have discovered ways of existing that we can't even imagine, ways of persisting through time, of experiencing duration, of relating to the flow of moments that are completely alien to our understanding. And yet all of it, the microsecond lives and the million-year lives, the fast and the slow, the brief and the enduring, all of it is part of the same universe, the same unfolding story. You're experiencing time in your particular way, at your particular scale. But you are part of a cosmos that contains all possible scales, all possible rhythms, all possible relationships with duration. Let's turn now to consciousness, to awareness, to the strange fact that the universe contains observers. You are not just a collection of atoms. You're a collection of atoms that knows it's a collection of atoms. You are matter that has become aware of itself. This is one of the deepest mysteries in all of science. How does consciousness arise? How do physical processes in the brain give rise to subjective experience, to the feeling of what it's like to be you? We don't know. Despite all our advances in neuroscience, despite our ability to map brain activity and trace neural pathways, we still don't understand how consciousness emerges from matter. But here's what we do know. Consciousness exists. Awareness is real. The universe contains systems that can observe, that can know, that can wonder about their own existence. And if consciousness can emerge here, on Earth, in human brains, then perhaps it can emerge elsewhere. Perhaps it has emerged elsewhere. Perhaps it emerged long ago in forms we wouldn't recognize, in substrates we haven't considered. What if ancient life developed consciousness? What if there were observers in the universe billions of years before humans evolved, looking up at their own skies, wondering about their own origins, asking the same questions we're asking now? There's something called the observer effect in quantum physics. The act of observation affects what is observed. At the quantum level, particles exist in superposition, multiple states at once, until they're measured. The measurement, the observation, collapses the superposition into a definite state. This has led some physicists to wonder about the role of consciousness in the universe. Does the universe need observers to become definite, to collapse from possibility into actuality? It's a controversial idea, and most physicists are skeptical. But it raises a profound question. What is the relationship between consciousness and physical reality? If ancient life developed consciousness billions of years ago, then the universe has contained observers for most of its history. The cosmos has been watching itself, knowing itself, collapsing its own quantum possibilities into definite states for eons. You are an observer. Right now, in this moment, you are the universe observing itself. Your awareness is not separate from the physical world. It is the physical world becoming aware of itself. And if consciousness is ancient, if it emerged long before Earth, then this process, this strange, miraculous process of matter becoming aware, has been happening for billions of years. Perhaps consciousness is not rare. Perhaps it's common, inevitable even, given the right conditions and enough time. Perhaps the universe naturally gives rise to observers, to systems that can know and wonder and question. And perhaps those ancient observers, wherever and whenever they existed, experienced the same sense of awe that you're experiencing now, the same wonder at existence, the same questions about origins and meaning and purpose. Let's consider whether life is inevitable. Given the right conditions, liquid water, organic molecules, energy sources, time, does life have to emerge? Or is it a fantastically unlikely accident, a cosmic fluke that might have happened only once in the entire universe? The mathematics of probability are tricky here. We only have one example, life on Earth. We don't know if it's common or rare, typical or exceptional, but there are reasons to think life might be inevitable, or at least highly probable given the right conditions. The laws of physics and chemistry are the same everywhere in the universe. The same elements exist. The same forces operate. The same reactions are possible. If you create the right conditions, if you have liquid water, organic molecules, energy gradients and time, then certain chemical reactions will happen. They have to happen. They're not optional. They're consequences of the laws of nature, and some of those reactions lead to increasing complexity. Simple molecules combine to form more complex ones. Complex molecules form structures. Structures begin to interact in ways that preserve and replicate patterns. At some point, the line between chemistry and biology becomes blurred. At some point, you have systems that can maintain themselves, that can reproduce, that can evolve. At some point, you have life. If this process is inevitable, if it's a natural consequence of chemistry and physics, then life should be common in the universe. And if life is common now, it was probably common in the past. Perhaps it emerged as soon as the universe cooled enough to allow complex chemistry. Perhaps it's been here almost from the beginning. This doesn't mean life is everywhere. It means life emerges wherever the conditions are right. And in a universe as vast as ours, with billions of galaxies each containing billions of stars, the conditions are right in countless places. The question is not whether life exists elsewhere. The question is how common it is, how diverse it is, how ancient it is, and if the emergence of life is a natural, perhaps inevitable consequence of the laws of physics, then the universe has been generating life for as long as the conditions have allowed, which might be a very long time indeed. There's a concept in evolutionary biology called convergent evolution. It's the observation that similar solutions to similar problems emerge independently in different lineages. Eyes, for example, have evolved separately dozens of times. Flight has evolved independently in insects, birds, bats and pterosaurs. Echolocation has evolved separately in bats and dolphins. The streamlined body shape for moving through water has evolved in fish, ichthyosaurs, dolphins and penguins. The same solutions emerge again and again because they work. Because they're good solutions to common problems. Because the laws of physics and the constraints of biology push evolution towards certain forms, certain strategies, certain designs. If convergent evolution happens on Earth, it probably happens throughout the universe. The same problems, how to sense light, how to move efficiently, how to process information, would lead to similar solutions on different worlds. This suggests that life, wherever it emerges, might follow predictable patterns. Not identical patterns, the details would vary based on local conditions, but recognizable patterns. Solutions that work, strategies that succeed, forms that function. If ancient life existed, it probably discovered many of the same solutions that life on Earth has discovered. Perhaps it developed photosynthesis, or something like it. Perhaps it evolved multicellularity, or something analogous. Perhaps it developed nervous systems, or information processing structures that served similar functions. The universe might be more predictable than we think. The space of possible solutions might be smaller than the space of imaginable solutions. Life might tend towards certain forms, certain strategies, certain patterns, and if that's true, then ancient life might not be as alien as we imagine. It might be recognizable, at least in principle. It might have solved problems in ways we can understand, because they're the ways that work, the ways that the laws of nature favor. This doesn't mean ancient life would look like Earth life. The details would be different. The chemistry might be different. The specific forms would be unique. But the underlying principles might be the same. The strategies for managing energy, for preserving information, for adapting to changing conditions, these might be universal or nearly so. Life might be the universe's way of exploring a particular region of possibility space, and that region might be smaller, more constrained, more predictable than we think. Let's think about complexity and how it emerges from simplicity. The universe began in a state of extreme simplicity. In the first moments after the Big Bang, there were no atoms, no molecules, no structures of any kind. Just a hot, dense soup of fundamental particles and energy. But the universe had rules, the laws of physics, the fundamental forces, the properties of particles and fields, and from those simple rules, complexity emerged. Particles combined to form atoms. Atoms combined to form molecules. Molecules formed structures. Structures formed systems. Systems formed organisms. Each level of complexity emerged from the level below it, following rules, obeying laws, but producing something new, something that couldn't have been predicted just by looking at the components. This is emergence. The whole is more than the sum of its parts. New properties, new behaviours, new possibilities arise when simple components interact in complex ways. Water molecules are simple, but when billions of them interact, you get waves, currents, whirlpools, patterns that don't exist in individual molecules but emerge from their collective behaviour. Neurons are relatively simple, but when billions of them interact in the right way, you get consciousness, thought, awareness, properties that don't exist in individual neurons but emerge from the network. Life itself is an emergent phenomenon. It arises from chemistry, but it's more than chemistry. It has properties, reproduction, evolution, adaptation, that don't exist in non-living chemical systems. If complexity emerges naturally from simplicity, given time and the right conditions, then the universe has been generating complexity for its entire history. And if ancient life existed, it had billions of years to explore the space of possible complexity. Billions of years for simple systems to become complex, for complex systems to become more complex, for new levels of organization to emerge. What might emerge from billions of years of evolution? What levels of complexity might be possible that we haven't even imagined? Perhaps ancient life discovered forms of organization, levels of complexity, emergent properties that we have no concepts for. Perhaps it explored regions of possibility space that Earth life hasn't reached yet, and might never reach. The universe is a complexity-generating machine. It starts simple and becomes complex. It explores possibilities. It discovers new forms, new patterns, new ways of organizing matter and energy. And life is part of that process. Life is one of the ways the universe generates complexity. Perhaps the most effective way. Perhaps the inevitable way, once certain conditions are met. If life is ancient, then the universe has been generating biological complexity for most of its history. The process we see on Earth, evolution, adaptation, increasing sophistication, might be a process that's been running for 10 billion years or more. You're part of that process. You're one of the latest expressions of the universe's tendency to generate complexity, but you're not the first. You're not even close to the first. Now, let's consider the fine-tuning of physical constants. The universe is governed by fundamental constants. The strength of gravity, the charge of the electron, the mass of the proton, the speed of light. These constants determine how matter and energy behave, how atoms form, how stars burn, how galaxies evolve. And here's the strange thing. If these constants were even slightly different, the universe would be radically different. Stars wouldn't form, atoms wouldn't be stable, chemistry as we know it wouldn't be possible. The constants seem to be fine-tuned for complexity, for structure, for the possibility of life. Why? We don't know. Maybe it's just luck. We happen to exist in a universe with the right constants, because we couldn't exist in a universe with different constants. Maybe there are countless universes with different constants, and we're in one of the rare ones that allows life. Or maybe there's something deeper going on. Maybe the constants aren't arbitrary. Maybe they're the way they are for a reason we don't yet understand. But here's what we can say. The universe we live in is capable of generating complexity. It's capable of producing stars and planets, and chemistry, and life. The fundamental constants allow for all of this. And if the constants have been the same throughout the universe's history, and we have every reason to think they have been, then the universe has been capable of generating life for as long as the conditions have allowed. If ancient life existed, it existed in a universe with the same fundamental constants we have now. It was subject to the same laws of physics, the same forces, the same constraints. But the early universe was different in other ways. It was denser, it was hotter, it had a different mix of elements. The first stars were different from modern stars. The first planets were different from modern planets. The chemistry might have been different. Not the fundamental laws of chemistry, those are determined by the constants, but the available ingredients, the typical conditions, the environments where chemistry could happen. Perhaps ancient life used different elements, different molecules, different chemical pathways than Earth life uses, not because the laws were different, but because the available materials were different. The early universe had mostly hydrogen and helium. The heavier elements, carbon, oxygen, nitrogen, iron, were created in stars and scattered by supernovae. It took time for those elements to become abundant. But life doesn't necessarily need the same elements we use. Life needs elements that can form complex molecules, that can store information, that can catalyze reactions. There might be other combinations that work, other chemistries that can support life. Perhaps ancient life used silicon instead of carbon. Perhaps it used ammonia instead of water. Perhaps it found ways to work with the limited palette of elements available in the early universe. Or perhaps it waited. Perhaps life couldn't emerge until the first supernova had scattered heavier elements into space. Perhaps there was a waiting period, a time when the universe was capable of supporting life but didn't yet have the right ingredients. We don't know. But the question is fascinating. The chemistry of the early universe was different, and that might have shaped what ancient life was like, how it functioned, what it was made of. Let's zoom out now and think about the structure of the universe itself. The universe is not uniform. It's organized into a cosmic web, filaments of galaxies separated by vast voids. Matter is concentrated along these filaments, with galaxy clusters at the intersections and enormous empty spaces in between. This structure emerged from tiny fluctuations in the early universe, amplified by gravity over billions of years. It's a pattern that spans the entire observable universe, a structure on the largest possible scale. And here's an interesting thought. This structure might have influenced where and when life could emerge. Life needs matter. It needs elements, molecules, chemistry. And matter is concentrated along the filaments of the cosmic web, in galaxies, in star systems. But life also needs energy. It needs stars, or other energy sources, and stars form in galaxies, which are concentrated along the filaments. So the cosmic web might be a map of where life is possible. The filaments are where the action is, where matter and energy come together, where chemistry can happen, where life can emerge. The voids, by contrast, are empty. Not completely empty. There are some atoms, some photons, but empty enough that nothing interesting happens there. No stars, no planets, no chemistry, no life. If ancient life existed, it existed along the filaments of the cosmic web. It emerged in galaxies, in star systems, in places where matter and energy were concentrated, and perhaps it spread along the filaments. Perhaps panspermia isn't just about life spreading from planet to planet within a single star system, or even from star to star within a single galaxy. Perhaps it's about life spreading along the cosmic web, from galaxy to galaxy, following the filaments of matter and energy. This would take an unimaginably long time. The distances between galaxies are vast, but if life is ancient, if it's been spreading for billions of years, then perhaps it's had time to explore not just individual worlds, not just individual star systems, not just individual galaxies, but the cosmic web itself. Perhaps life is a feature of the universe's large-scale structure. Perhaps it emerges wherever the conditions are right and then spreads, slowly but inexorably, along the pathways defined by gravity and matter and energy. There's an even stranger thought. What if the universe itself has properties we associate with life? The universe is organized. It has structure. It processes information. The state of the universe at one moment determines its state at the next moment, following rules, evolving over time. The universe maintains boundaries, the edge of the observable universe, the event horizons of black holes, the boundaries between different regions of space. The universe responds to its environment. Matter and energy interact, influence each other, change each other. These are properties we associate with living systems. Does that mean the universe is alive? Probably not, at least not in any conventional sense. The universe doesn't reproduce. It doesn't evolve through natural selection. It doesn't have metabolism or homeostasis or any of the other characteristics we typically use to define life. But the question points to something interesting. The line between living and non-living is not as clear as we might think. There's a continuum, a spectrum of organization and complexity, and life is somewhere on that spectrum, but it's not completely separate from non-living systems. The universe generates complexity. It creates structure. It processes information. And at some point, in some places, under some conditions, that complexity and structure and information processing becomes what we call life. Life is not separate from the universe. Life is what the universe does, in certain places, under certain conditions. Life is the universe organizing itself, knowing itself, exploring its own possibilities. And if that's true, then ancient life is not an anomaly. It's not a strange accident that happened once or twice in cosmic history. It's a natural expression of what the universe is and what it does. The universe generates complexity. It always has. It always will, until the very end, until entropy finally wins and everything dissolves into uniform equilibrium. And life is one of the forms that complexity takes. Perhaps the most interesting form. Perhaps the most significant form. Perhaps the form that allows the universe to know itself, to observe itself, to wonder about itself. If ancient life existed, and the more we think about it, the more plausible it seems, then the universe has been engaged in this process of self-knowing for most of its history. Let's think about chaos theory and emergent phenomena, because they're relevant to understanding how life might arise and spread. Chaos theory studies systems that are highly sensitive to initial conditions. Small changes in the starting state can lead to vastly different outcomes. The classic example is the butterfly effect. A butterfly flapping its wings in Brazil might, through a chain of cause and effect, influence the weather in Texas weeks later. Chaotic systems are deterministic. They follow rules, but they're unpredictable in practice because we can never know the initial conditions with perfect precision. The weather is chaotic. The solar system is chaotic over long time scales. Many biological systems are chaotic, but chaos doesn't mean randomness. Chaotic systems often produce patterns, structures, regularities. They explore certain regions of possibility space more than others. They have attractors, states or patterns they tend toward. And sometimes from chaos, order emerges, patterns form, structures arise. This is emergence, the spontaneous appearance of organization from disorder. Life might be an emergent phenomenon arising from the chaos of chemistry. Given the right conditions, given enough time, given the sensitivity of chemical systems to initial conditions, patterns emerge that can maintain themselves that can reproduce, that can evolve. And once those patterns emerge, they're stable. They persist. They spread. They become more complex. If life is an emergent phenomenon, then it might be inevitable, or at least highly probable, given the right conditions. You don't need to carefully design life. You don't need to assemble it piece by piece. You just need to create the conditions where emergence can happen, and then wait. The early universe was chaotic. Matter and energy were distributed unevenly. Fluctuations were amplified. Structures formed, stars, galaxies, planets, and on some of those planets, or in some of those environments, the conditions were right for chemical emergence, for patterns to form that could maintain themselves, for life to begin. If this happened once, it probably happened many times. If it happened in the recent universe, it probably happened in the ancient universe too. Emergence is one of the universe's fundamental tricks. It's how complexity arises from simplicity. It's how new levels of organization appear. It's how the universe explores possibilities. And life is perhaps the most remarkable example of emergence we know. From simple chemistry, following simple rules, something new appears, something that can grow, reproduce, evolve, adapt, eventually think and wonder and ask questions about its own origins. If ancient life existed, it was an emergent phenomenon arising from the chaos and complexity of the early universe. And once it emerged, it persisted, spread, evolved, explored new possibilities. The universe has been running this experiment for billions of years. The experiment of seeing what emerges when matter and energy interact in complex ways. The experiment of exploring the space of possible patterns, possible structures, possible forms of organization. And you are part of that experiment. You are one of the patterns that has emerged, one of the structures that has formed, one of the ways the universe has organized itself. As you lie here now, feeling the weight of your body, the rhythm of your breath, the quiet hum of your thoughts, consider what you are. You're a dissipative structure, managing energy flows, creating local order at the cost of increasing entropy elsewhere. You're an information processing system, preserving and transmitting patterns that might be billions of years old. You're an emergent phenomenon, a pattern that arose from chaos and complexity and has maintained itself through time. You're an observer, a point where the universe becomes aware of itself. You're a temporary island of organization in a universe trending toward disorder. But your existence is not futile. You are part of the universe's exploration of what's possible. You are part of the story that began long ago and continues still. The extremophils show us that life is resilient, adaptable, capable of surviving in conditions we once thought impossible. They show us that life is not fragile but robust, not delicate but persistent. The laws of thermodynamics show us that life is not a violation of physics but an expression of it, a natural consequence of how energy flows through complex systems. The mathematics of emergence show us that complexity arises naturally from simplicity, that patterns form spontaneously when conditions are right. The fine-tuning of physical constants shows us that the universe is capable of generating complexity, that it has the right properties to allow for structure, chemistry, life. All of this suggests that life is not rare, not unlikely, not a cosmic accident. Life is what the universe does. Life is natural, perhaps inevitable, certainly persistent. And if life is natural and persistent, then it's probably ancient. It probably emerged as soon as conditions allowed. It probably spread wherever it could. It probably explored countless forms, countless strategies, countless ways of being alive. The story of life is not the story of Earth. Earth is one chapter in a much longer story, a story that might stretch back to the beginning of time. You are part of that story. The atoms in your body are ancient. The information in your genes might be ancient. The patterns of organization that make you alive might be ancient. You are not separate from the cosmos. You are the cosmos experiencing itself, knowing itself, wondering about itself. And that cosmos is old. It's been generating complexity, creating structure, exploring possibilities for billions of years. Life is part of that process, perhaps the most important part, perhaps the part that gives it all meaning. So rest now, knowing that you are part of something vast and ancient, something that transcends any individual life, any single world, any particular moment in time. The universe is engaged in a grand experiment, an exploration of what's possible when matter and energy interact in complex ways. And you are part of that experiment. You are one of the possibilities being explored, one of the patterns being tested, one of the ways the universe has organized itself. And whether life is 10 billion years old or 4 billion years old, whether it emerged once or countless times, whether it's common or rare, the fact remains. You are here. You are alive. You are aware. And that is extraordinary. That is miraculous. That is worth contemplating as you drift towards sleep. The universe is old and you are young, but you are made of the universe, and in that sense you are as old as time itself. You are ancient and new, temporary and eternal, a single note in an endless song. Sleep well, knowing that the story continues. The universe is still exploring, still creating, still discovering new possibilities. And you are part of it all, now and always.